Welcome back to the lecture series on CCNA Introduction to Networks. This is Module 5 and we will go over the number systems. If you would like to know the previous modules and would like to learn from it, there is a series of videos that I have posted on my YouTube channel, and they are also linked to a playlist, and I will leave the link below and you can go ahead and watch those modules so that you have a better idea about the previous modules and what we have covered. In this module, we will learn how you can convert between decimal, binary and hexadecimal systems. The binary number system can be described as a calculate numbers between decimal and binary systems, while the hexadecimal system is calculate numbers between decimal and hexadecimal systems. So those would be our two objectives in this particular module. The binary number system. The binary number system is used in especially IPv4 addresses. The binary numbering system consists of ones and zeros, and they are called bits. Decimal numbering system consists of digits 0 to 9. Hosts, servers, and network equipment using binary addressing to identify each other. Each address is made out of string of 32 bits, which is 8 times 4, divided into 4 sections called octets. Each octet contains 8 bits. Therefore, that's why we call it octet. Octa mean 8, and 8 bits consists of 8 bits mean octet, and separated by a dot. For ease of use by people, this dotted notation is converted to dotted decimal. So for example, here 192.168.10.1. Each one of these, for example, 192 is a 1 octet, and 168 is the next octet, 10 is the next octet, and 1 is another octet. So these are all octet because there are 32 bits, which are 8 times we have 4, 1, 2, 3, 4, and the total of 32 bits, and each one of them consists of 8 bits. So that's what this means. There's a video posted on my YouTube channel that is directly from Cisco NetAcad, and it is made by Cisco. In case you do not have access to the course material through Cisco, I have posted it on my website, so as well as on my YouTube channel. I will leave a link in the description so you can click on it and watch that video. I will not cover any of these things right now because you can just go ahead and watch that. So I'm going to skip to the next slide. The binary positional notation. The positional notation means that a digit represents different values depending on the position the digit occupies in the sequence of numbers. So the decimal positional notation system operates as shown in the tables below. Like for example, we have the tens at the top, and we have 3, 2, 1, 0. So it's go from when you go from left to right, it decrease the positional number. And here we have 10 to 3, which is 1000, and 10 to 2, which is 10, which is 10. Here 10 to 1, which is 10, and 10 to 0 is 1. So 1000, 100, 10, 1. So 10 to 2 is 100. So if you look at that as a positional value, so we have 1000, 100, 10, and ones. And if in decimal number format, it will be 1, 2, 3, 4. And when you calculate it, 1 times 1000 is 1000, 2 times 100 is 200, 3 times 10 is 30, and 4 times 1 is 4. So as a result, we're going to get it 1, 2, 3, 4. I know when you go through these slides without actually doing the calculations, it may be like over your head and what is going on. Like I mentioned, I will leave videos below and I will make a separate video on how these calculations work. But just for now, in this particular module, we'll just go through these slides and just to understand the basic concepts first, and we will learn about how to do these calculations later. Next, we're going to look at the binary positional notational system operates on another table. In here we see the 2s. In this case it's binary. Like in here we had 10s at the top, and here we have the 2s at the top. So that means we are instead of taking 10 to the power, here we are taking 2 to the power. So positional number here we're going to be 7, 6, 5, 4, 3, 2, 1, 0. So there's 8 sections, and we have 2 to the 7, 2 to the 6, 2 to the 5, 2 to the 4, 2 to the 3, 2 to the 2, 2 to the 1, and 2 to the 0. So 2 to the 7 will give you the positional value of 128. Remember, in computing 128 bits or 256 bits, that will be the next value. This is 2 to the 8 going to be give you 256, and 2 to the 7 will give you 128. So that's where it come from. So this is 2 to the 7, which is base is 2, and its power of 7 is going to give you 128. So it's going to end up with 128, 64, 32, 16, 8, 4, 2, 1. And with the positional value, we can calculate this as 1 times 128, 1 times 64, and so on and so forth. So if you have a binary number in this example as 11000000, and you want to know what the binary value of that number, what we're going to do, actually, the very first bit going to have 128, and we have one of them, so 1 times 128, plus we have 1 times 64, we have another bit here, and here there is no bit, so we're going to say 0 times 32 is 0, and 0 times 16 is 0, 0 times 8 is 0, and 0 times 4 is 0, 0 times 2, which is this position, which is 2, is 0, and 0 times 0 is 0. And then you add them up. So 128 plus 64 equal to 192, and everything else is zeroed out. So that means the binary value 11000000 is equal to 192 in the decimal system. So the computer will read this 192 value as 11000000 and use this type of calculation to understand that it is 192. And this is very important for your Cisco CCNA exams. You will be given some calculations to do during the exam, and you should be able to convert a binary value into decimal and decimal value into binary. And I will show you how you can do the other way around as well. So how do you going to convert the binary to a decimal? Let's convert the IP address 192.168.11.10, which all the Cisco devices or any other intermediary or end devices understand as 1100000010101000, so on and so forth. So when we give our networking devices or end devices this 192.168.11.10 address, what it actually reading is this value at the top. I'm going to go back. This value at the top. So let's convert that into the decimal format, which we understand, where we have 1, 2, 3, 4 octet. So the first value is 11000000. So that means 128th positional value, we have 1, 64 we have 1, 32 there's none, 16 we have none, 8 we have none, 4 we have none, 2 we have none, and 1 we have none. That means we're going to multiply 1 times 128, 1 times 64, and there's none, 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 none here, and then none here. So that means on the first position, we have 128 plus 64, which add up to 192. And then the second octet, we have, we need to get the value for that octet. So to do that, on the binary, we have 1010100. So again, we're going to use this table. On the positional value of 128, we have 1. Positional value of 64, we have 0. We have 30. We have 1 on 32, and we have none on 16. We have 1 on 8, and none on the rest. So that means 1 times 128 give you 128, and we have nothing on 64, and we have 1 on 32, and we have nothing on 16, and we have 1 on 8, and nothing for the rest, 4, 2, 1. So that means we're going to add 128 plus 32 plus 8, which is going to give you 168. So that means we have 192 for the first octet, 168 for the second octet. Now look at the third octet. So third octet, again, bunch of zeros at the front, 4 zeros, 1, 0, 1, 1. So on the positional value of 128, we have zeros, 0, 0, 0, all the way from 128, 64, 32, and 16, all zeros. Then on 8, we have 1, 4, we have 0, 2, we have 1, and 1, we have 1. So that means 0 times 128, 0 times 64, 0 times 32, 0 times 16, which all resulted in zeros. Then we have 1 times 8, 0 times 4, 1 times 2, and 1 times 1. And if you add 8 plus 2 plus 1, which is going to give you 11. So the third octet going to be 11. The fourth octet, we have 4 zeros at the front and 1 0 1 0. So that means positional value 128 all the way to 16 is 0. So 0 0 0. And then we have 1 8 and none for the fourth, and 1 on the second positional value, and none for the last one. So that means zeros at the front here all the way to positional value 16, and then we have 8 and we have none here and 2 here, and that's it. So that means 8 plus 2 will give you 10. So in here, this binary value that understood by our end devices and intermediary devices and networking devices and computer systems can be converted into 192.168.11.10. So we have that 1, 2, 3, 4 octet that was obtained by that binary value. This is a really good slide that explains how these conversions work. And if I were you, and if you're studying for exams, I would go through this table and do some calculations. You can create a random binary number or generate a random binary number from the internet, like a calculator, for example, and then just try to convert it into the decimals using a table like this. And more you do it, and more you get used to converting it. So let's look at how you can do decimal to binary conversion, which is the opposite of what we did. So the binary positional value table is useful in converting dotted decimal to IPv4 addresses to binary. So what we're going to do, we're going to start in the 128th position, the most significant bit, and is the decimal number of the octet n equal to the greater than or equal to 128. So what that means is basically we're gonna look at the first octet value. Let's say I have a IP address. Let's go back to the IP address here. Let's say we have 192 here, 168.11.10, right? So the first octet we have 192. The first thing we're gonna look at is look at the 192 and see, is it greater or less than 128? Because that's the first positional value, right? So 192 is greater than 128. Therefore, this is going to be a 1 here. So if there is no record, if there is no, it is not greater than that one, that value, that means we're going to put a 0 here. But because it is, if it is less than, we're going to put a 0 here. But because if it is greater, in this case, if you look at it, is 192 is greater than 128, we're going to put a 1 there. I will explain this in a different slide in more detail, and I will also do a separate video on these conversions. I'm doing on a whiteboard or by hand so that you could understand. But for now, just remember, you only put a value here as 1 if the value you're looking at on the octet is greater than or equal to. And if not, we're going to put a 0 there. And that's how you go through this process of converting the decimal to binary. And next few slides, we will look at how you exactly do it. And I will also post a video on that. For now, just remember, when you're converting from decimal to binary, you look at the starting position and you look at the octet And if the octet value is greater than or equal to, we're going to put a 1. And if the octet value is less than 128, we're going to put a 0. Or if you go to the next positional value, you could do the other option. And then you're going to keep going on and on and on until it, all been marked out. So let's do some conversions and understand how it works. Remember that 168, the first octet on that IP address? Let's convert that into a binary value. So as I mentioned in my previous slide, we're going to look at that 168 and we're going to look at the first positional value. And it's going to be 128, and we have 168 as the our value that we need to convert. Is it greater or equal to 168? Well, it's greater. And it's greater or equal, right? So we're going to put a 1 here. And then what we're going to do, before we move on to the next positional value, which is a 64, we're going to take this 168 minus the 128, because we already have calculated that 128. So if you go 168 minus 128, it's going to equal to 40. So 168 minus 128 equal to 40, because we have already taken into account that 128 on the first positional value of 128. Now we have 64. The positional value of 64 is going to be compared against that remaining value of 40. Because 168 minus 128 equal to 40. And when you compare that 40 to the positional value of 64, it is actually, the 40 is less than 64. That means we cannot satisfy that positional value, so we're going to put a 0 there. We're going to move on to the next one. The next positional value is 32. And we still have that 40. And we're going to look at if the 40 is greater than or equal to 32. Well, the 40 is actually greater than 32. So we're going to put a 1 in here. And what's going to happen is we're going to take that 40 and we're going to minus 32, because the positional value is 32 and we have a remaining value of 40. So from the previous positional value, and we're going to minus that from this positional value. So that's going to be 8. So we're going to move on to the next positional value. And in this case, it's going to be 16. And we have a remaining of 8. Is 8 is greater than or equal to 16? No. So we're going to put a 0 there and we're going to move on to the next positional value. And on the next positional value, we have 8. Now we have a remaining 8 and we have a positional value of 8. So we're going to check is the 8 is greater than or equal to that positional value. And it is exactly what the positional value is turned out to be. So it's 8 is equal to 8. So we're going to put a 1 here because it's greater than or equal to 8. And then if you take that 8, and because we are at the positional value of 8, and if you remove that 8, because 8 minus 8, because you have a remaining value, and your position, you're going to minus that from the positional value, that which you put 1 here, and you're going to end up with 0. So that means the remaining positional value is going to end up is 0, 0, 0, because 0 going to be less than, always going to be less than all of these positional values. So as a result, when we convert 168 into a decimal, the binary value, 168 decimal value into binary value, we're going to end up with 1, 0, 1, 0, 1, 0, 0, 0. One of the things that you should have noticed here is that once you have reached that equal position, which is right here in this example, in the 8th position, we reach equal. You don't even need to look at the fourth, second, and first positions. They're all going to be 0 because the value here turn out to be 0. So that's pretty neat trick that I use when I'm converting it. If I have 1, 0, 1, and then here it's all equal to 16, I'm going to turn everything else into 0. You don't even need to look at that, because if you go through this process more times, you will realize that you know it's pretty easy to convert the rest once it's reached that equal to that positional value. In other words, if your remaining value is equal to a positional value, The rest on the right hand side going to be 0, because what you left with is 0. That's a neat trick that I use during exams and quizzes. So this slide is very important, and you should know how to look at it and do the calculations just like the previous slide. And again, I will post a video later, so we'll move on to the next slide. The IPv4 addresses used by routers and computers only understand binary, while humans work in decimal. So it is important for you to gain a thorough understanding of these two numbering systems and how they are used in networking. For example, when you have an IP address of 192.168.10.10, this is what humans understand. This is what you and I will be entering into Cisco devices as well as end devices. However, the computers and switches and network systems, including routers and everything else in between, understand the values like this. So that's why you need to understand the differences between the binary and decimal systems. Next, we're going to talk about hexadecimal number system, which is used in the IPv6 addressing scheme. To understand IPv6 addresses, you must be able to convert hexadecimal to decimal and back and forth. Hexadecimal is a base 16 numbering system using a digits 0 through 9 and letters A to F. It is easier to express a value as a single hexadecimal digit than a 4 binary bit. Hexadecimal is used to represent IPv6 addresses and MAC addresses. And one of the key difference between hexadecimal and the binary system is that it allows more IP addresses within that system. IPv4 addresses, we are kind of running out of it, but IPv6, what they are doing is they are using the hexadecimal system with base 16 to end up with more IP addresses so that we have a lot of room to play around. If you look at the right hand side of your slide, you will see the decimal numbering system, which is 0 to 15. And then we have the binary numbering system showing here with the 0 to 15. And you have the hexadecimal system, how these numbers are represented in hexadecimal. For example, if you want to represent number 11 in binary, it's going to be 1011, but in hexadecimal, it's going to be B, the letter B. As long as it's the letter B, it should be fine. So it doesn't matter it's a capital or simple B. In this diagram, it has a capital B. But if you want to represent, like for example, number 14 on decimal is just 14, but in binary 110, but in hexadecimal it's going to be E. So that is a really key concept that you need to understand. So a hexadecimal goes from 0 to 9 and A to F. And that's how you represent hexadecimal. IPv6 addresses are 128 bits in length as opposed to 32 bit. Every 4 bit is represented by a single hexadecimal digit. That makes the IPv6 address a total of 32 hexadecimal values. The figure on the right hand side shows the preferred method of writing out an IPv6 address, with each X representing 4 hexadecimal value. Each 4 hexadecimal character group is referred to as a hextact. Remember octact? So octact is for the IPv4 addresses. This is hextact because it is have 32 the hexadecimal values total. So for example, in here, we have an IPv6 address represented as X, these 2 dots. Instead of having like single dot in IPv4 type, in an IPv6, we're going to use this 2 double dot thing. And then these values represent on the bottom as like here, FFF, 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 like just like this here. So this is how you convert between those numbers into the IPv6, the hexadecimal numbers. So this diagram is a really good diagram that you should look at if you would like to have a quick overview of how those hexadecimal numbers being converted. There is a video on your Cisco NetAcad Academy that you can watch on how you're going to convert these hexadecimal values. I will be leaving a link on my description in this video because I'll be posting that video on my YouTube channel just in case you do not have access to NetAcad. And the video title going to be converting between hexadecimal and decimal numbering system. And you should go ahead and watch that video so that you can understand how it works. So decimal to hexadecimal conversions follow the steps listed here. So how it works is we convert the decimal number to 8-bit binary strings, divide the binary strings in groups of 4 starting from the rightmost position, convert each 4 binary numbers into their equivalent hexadecimal digit. For example, if you have 168, which is the first octet of that IP address, IPv4 address, right? And you want to convert into hex using these 3 steps. What we're going to do is we're going to take that 168 and convert it to binary, which is 10101000. Then we're going to take that into 2 groups of 4 binary digits, which is 1010 and 100. And 1010 in hex is A, and 1000 is in hex is 8. So 168 can be represented as A8 in hexadecimal. So let's go over this again. So we have 168 and we need to convert it all the way into hexadecimal. So 168 in binary is 10101000. Then we're going to take that value in 2 groups of 4 binary digits. So it's going to be 1010 and then we're going to have 1000, 1 and 3 zeros. So 1010 in hex is A. So if you go back to that table that I showed you before, right here, the A is 1010, right? So remember that table, A is 1010. So that's why it is represented as A here. So 100, if you go back to that table, you'll see the hex value going to be 8. So if you go back here, the hex value 8 is 1000. So that's why when we have 1000, we're going to use 8. And therefore, the 168 in hexadecimal can be represented by A8 notation. So hexadecimal to decimal conversions follow the following steps. So what we will do in this case, we're going to go backward now. We're going to take the hexadecimal value and we're going to convert that into decimal. To do that, we're going to convert the hexadecimal number to 4-bit binary strings. Create 8-bit binary grouping starting from the rightmost position. Convert each 8-bit binary grouping into their equivalent decimal digit. For example, let's say we have D2 and we want to convert into into decimal. So what we're going to do is we're going to take the D2 and in 4-bit binary string, we're going to split it into 2, which is going to be 1110 0010. Again, you can go back to that table that you've seen before, and you can use that to look at, convert this into 2. For example, let's go back and look at it quickly so that you have a better idea. So if you go back in here, you'll see in here we have D2, right? So D is 1101 and 2 gonna be 0010. So let's see if that's the case. So we have D2. So D is 1110 and 2 is 0010. And 1110 and 0010 is 111 100010 in an 8-bit grouping. And then you can convert that into equivalent of 210 or 210 in decimal. So D2 is 210 in decimal. Again, if you just go through these slides and if you just listen to what I have to say about these conversions, you're probably not going to understand this completely, especially on an exam where you need to convert these numbers back and forth between these different numbering systems. So what I would recommend is that you go ahead and pick some numbers random and then start converting them and see if you get the same value. I may find some number generating websites where you can check your answers and leave the link in my the video description. And also I will leave a video later going through these conversions so you can have a better idea about how to do them. So what did we learn in this lecture? We learned that binary is a base 2 numbering system that consists of numbers 0 and 1 called bits. Decimal is a base 10 numbering system that consists of numbers 0 through 9. Binary is what host, servers, and intermediary networking equipment uses to identify each other. Hexadecimal is a base 16 numbering system that consists of numbers 0 through 9 and letters A to F. And this hexadecimal system is the reason why we have the IPv6 and addresses and MAC addresses, and it allowed a greater range of numbers to be generated as opposed to IPv4 addresses. IPv6 addresses therefore are 128-bit long, and every 4 bit is represented by a hexadecimal digit for a total of 32 hexadecimal digits. You need to understand how to convert hexadecimal to decimal, and you must know how to do it by converting that into hexadecimal to binary, then converting that into binary value into decimal. And you should also know how to convert decimal to hexadecimal. What you need to do for that is to convert the decimal to binary and then to binary to hexadecimal. And that's everything for this brief lecture today. And please remember that just going through this lecture over and over or rewatching this video probably not going to make you good at writing those exams and answering those exam questions and converting those values. What I would recommend is go ahead and pick some binary values, decimal values, and hexadecimal values and start converting back and forth until you are really good at it. This is a really good overview. However, you need to be able to understand how you can convert between those numbers without using calculators, because this does show up on CCNA as well as CCNP exams, and as students and professionals you should be able to convert between those numbering systems. And that is everything for this module. I will post a new module in next few weeks. And please remember to thumbs up this video and subscribe to my channel. And until next time, have a nice day.